And hello, everyone, to today's online seminar on interval methods and control engineering. And it's my great pleasure to welcome today Antoine Hugo. Antoine received his engineering degree in 2020 in Toulouse. And since November 2021, he's now been working as a PhD candidate, on the one hand at ONERA, and on the other hand also at the c'est quoi, l'Institut de recherche en système électronique embarqué. And yes, it's my great pleasure to have you here. And yes, that you can present your talk on filtered high-gain interval observers for LPV systems with bounded uncertainties. Antoine, the floor is yours.
Okay, thanks a lot. Thanks for having me in this seminar. And thanks for the introduction also. So today I will present you the work that I've done for an article that will be presented next week in the conference on decision and control. And it is talking about filtered high-gain interval observer for LPV system with bounded uncertainties. So to give you the outline of the presentation, I will start by introducing the topic and the key concept behind the work. I will move on next to the problem statement, and we will arrive to the two main parts of this work, which are the design of the high-gain interval observer in the first time. In a second time, its filtered version that will be here to reduce the noise impact, as we will see. And I will finish the presentation by giving you some simulation results that I have come up with. So this work deals with the problem of state estimation of uncertain system, which can be complex in certain cases. There are a lot of different approaches that exist in the literature. For instance, in the stochastic framework, we can cite all the Kalman features and their extensions, which are really popular. And from the deterministic side, we will mainly focus during this presentation on high-gain observers and interval observers, but there are also other techniques that exist in order to do some robust state estimation. So in order to talk a little bit more about the two types of observer that will have interest during this presentation. So first, I will introduce the high-gain observer, which had become really popular because of three main reasons. First one, it is really easy to design because it is based on the classic Benberger structure of observers. The other advantage is that it can be tuned easily by a unique parameter theta that can tune the convergence rate and also the robustness of the estimations. However, it comes with two main drawbacks. The first one is the sensitivity to measurement noise. So if the system is too noisy, the convergence of the observer will still be exponentially, but the ball will be bigger. And the second drawback is the peaking phenomenon that happens during transient periods. So high-gain observer gives point-wise estimation of the state of the system. And we will see also interval observer that can give an estimated interval in which the system might belong. Interval observer assumes usually all the time that the uncertainties are bounded and that we know. So we don't know how the uncertainties vary, but we know that they are bounds and we know they're bounds. The main advantage of interval observer is that the inclusion is guaranteed. So by inclusion, I mean that the state of the system will always be included in the estimated bounds of the observer, represented here by X underbar and overbar. Underline and overline. The main drawback of those type of observer is the complexity of design. And we will see that it's really hard to obtain the cooperativity of the error dynamics, which is what guarantees the inclusion. And I will just talk about this concept right after doing the presentation. So the objective of this work was to combine both methodologies of high-gain observer and interval observer in order to create a high-gain interval observer that is quite simple, simple enough, I would say, to design, and also have the property of arbitrarily fast convergence given by the high-gain methodology. There already exist some designs of high-gain interval observers. So the aim was to improve what has already been done. For instance, I have taken into account in this work the measurement noise, which can really degrade the precision of the estimation of the high-gain observers. And so that's why a filter, I present the solution with the filter in which that will allow to mitigate the measurement noise. And there are also some other issues that has been treated, such as the real-time implementation issue that was happening in the mentioned paper. It was due to the change of coordinates that we will see why we use a change of coordinates and what is new in this one. So I have talked generally about high-gain observer and interval observers. I will now dive a little more in depth with them and focusing more mathematically on how to design them. So for high-gain observers, they are commonly designed for systems that are diffeomorphic to the system presented by one, which is it is a partially linear system that is in canonical observability form. And for those type of system, we are able to design a high-gain observer represented by the dynamics 2, and in which we have an observer gain L that is parameterized by a high-gain parameter theta and a gain K that is K is only here to ensure the stability of A minus KC. And then with theta, by augmenting theta, we are able to make the dynamics much faster, which yeah, that's the point. Some results can also be obtained for unstructured system, but we will have to take in consideration more hypotheses. And one thing that I didn't, I've talked about it, but high-gain observer provide an exponentially stability convergence of the state estimation. So the error converge exponentially. Now to talk about interval observers. The main the design of interval observer mainly is mainly based on monotone systems, and a monotone system is a system in which its solution preserves the relation order with respect to the initial conditions. And the other key concept is cooperativity, as I talked about. And a system, as presented here, is said to be cooperative if the state matrix is Messler. And Messlarity is that all the off-diagonal coefficients are positive. And the additional input must be also non-negative. So cooperative is important, but we don't need the system to be cooperative. It's not necessary. But we need the estimation errors to be cooperative. And that's the main point to prove the inclusion of the state inside the estimated bounds. And here is a quick example of how to design an interval observer for a linear system represented by equation 3 with a disturbance D that is assumed to be bounded. And we can obtain, for the dynamics of the interval observer. And note that for interval observers, we always have two different dynamics, one that is for the upper bound and the other one for the lower bound. At least we will have to, we will need to have two dynamics in order to represent an interval. Okay, so now we will move on to the problem statement. So in this work, we consider some linear parameter varying systems, such as presented by equation 5. So why did we choose this type of system? It's because most of the linear system can be exactly transformed into LPV systems. And so by considering this class of system, we stay quite general in the design of the observers, in the class of system considered. And so for when we have LPV system, we have a scheduling vector that is named rho here, and that will be considered as non-measurable. So it will be considered as an uncertainty for us. But we will know how we will know the bounds of this scaling vector. The uncertain matrices can also be decomposed as a linear combination of the components of the scaling vector. And there is also a nominal part. And so we can note that this type of system can be represented also as a linear parameter, as a partially linear system, like equation 6, which looks like a bit like to the class of system considered for Huygens observers. And it will have also the advantage to simplify a bit the notations. So we will consider now equation 6, which is equivalent to 5 when phi is taken as, I don't know if you can see it. Sorry. But yeah, phi takes into account the uncertainties related to the scaling vector and also the input. We will have to consider three different assumptions for this work. First one is that as we want to build an observer, we need the system to be observable. So the pair A0C must be observable. The second assumption is that the input is bounded. And this is not really restrictive because most of the time when systems are controlled, their control law are such that the input is bounded. So it's not really an issue. And the third assumption is that we know the bounds of the uncertainties. And the considered uncertainties are the initial state, the scheduling vector, the disturbance, and the noise. So for all those uncertainties, we will consider that they are bounded by known terms. Note that in this definition, we define the intervals as in the center radius form, which is equivalent to the upper and lower bounds that are commonly used in the design of interval observer in the literature. So these are the three main assumptions that are required. So now I will move to the design of the Huygens interval observer, so the one that does not yet take into account the measurement noise. So first, we need to base the design on the Huygens observer. We take the dynamics equation 7, in which we have an observer gain L that will be parameterized by the Huygens parameter theta. So L must ensure the cooperativity, the stability of the system, of the observer. But if we want to design also an interval observer, we need to make the state matrix to be Messler. And this is in order to ensure the cooperativity of the system, of the error dynamics. Usually, it is really difficult in practice to satisfy both conditions at the same time. And so what is done commonly is that a change of coordinate is used in order to ensure the cooperativity of the aerodynamics, but in the new base. So we will need to design a change of coordinates. There are three main steps to follow in order to design this type of observer. First one is to compute a gain L such that the system, the observer, the high gain observer, is stable. So in order to do that, we need A0 minus LC, the state matrix, to be Hurwitz. And we will also need to impose that it has distinct poles, and we will see why later. And those poles will be parameterized by theta. And so as we have observability, everything we will be able to design such gain L. And we will also need to ensure that the second line, the second bullet is satisfied. It is because the considered system is not structured in our hypothesis. And so we need to satisfy this. The gamma phi here is the Lipschitz, sorry, the Lipschitz constant of the non-linearity phi that removes the non-linear terms. Once we have that, if we design the gain L such that we have this, we will ensure both the stability of the observer and that the state matrix is diagonalizable over the field of the complex. And this diagonality, sorry, will be used in order to design the change of coordinates. So the change of coordinates will be made through the operator omega, which is time varying, and it depends, sorry, on the eigenparameter. So, depends on the eigenparameter theta, the imaginary part of the eigenvalues, and the eigenvector b, such that when we derive the observer dynamics in the new base, here, we have the state matrix that is now diag of theta xi, which is by construction Hurwitz and Messler. And this will allow to ensure the cooperativity of the aerodynamics in the new base. And I will show you later why. Once we have the dynamics on in the new base, we are able to design an interval observer based on this by considering the bounds of the uncertainties. And so we will be able, as we define some center and radius definition of the intervals, we will be able to have both dynamics for the center and the radius for our observer. So I arrived then to the main theorem of this work, which is the theorem that presents the Huygens interval observer. So basically, it says that the equation 8 here is an interval observer for the Huygens observer, which was 7. And so it has two dynamics, one for the center, one for the radius. And we have the state matrices that are Hurwitz and Messler by constructions. And we have some additional inputs that differs between the two dynamics. So the center will more represent, will more estimate, I will say, the nominal part of the system, whereas the radius will take into account all the uncertainties we have for our system. And we have the great property to have inclusion. So it means that the state of the Huygens observer will belong to the estimated state of the state of the Huygens observer will belong to the estimated bounds by the Huygens interval observer. And to go back and forth to the original And the new base is done through equations tens. So we just have to care about the imaginary parts of the numbers, because the new base can be imaginary, complex. Sorry. So now we will just jump into the analysis of this observer, first by proving that we have the cooperativity. So for that, we need to consider first the upper error dynamics, which is given here. And it is the sum of the center and radius dynamics. And we subtract the, the eigenobserver dynamics and everything in the new base, in the Z base. So we see that we arrive to these terms, and all of these terms can be grouped in order to form positive terms. So we first look at the disturbance, the terms related to the disturbances here, and this one, it can be proven that it is greater than 0. Same for the second line here, and the same for the last line. So now, if we have, as all of the term except diact xi are positive, if the state matrix is Messler, which is the case, and if we have the initial error that is positive, then the error dynamics will be cooperative, and thus we will have inclusion, because it will be the same, I didn't write it, but it is the same for the lower bound dynamics. So this way we prove that we have an interval observer that satisfies an inclusion property. We also need to show that the radius won't diverge, because it is not guaranteed directly. As we can see here with the dynamics of the radius, in the term psi r, there is an homogeneous term, ZR. And so that's why a proposition has been formulated that is a sufficient condition. And to make it simple, a certain matrix that is on the second line here of the proposition, we have to check that this matrix is Hurwitz. So it is quite easy to check. And what is the idea behind this proposition is that the uncertainties related to the scheduling vector that are reflected in the AI matrices. So we have to make sure that those uncertainties are not really are not preponderant with respect to the observer dynamics. That's the idea behind this proposition. So at each time we want to design such observer, the eigeninterval observer. So we need to check that we need to make sure that L makes the system stable and diagonalizability of the state matrix. And then after that, we also need to check that we have the non-divergence of the radius dynamics. So it is an additional step before saying that the observer will work as intended. Okay, so I will now move to the presentation of the filter eigeninterval observer. So as we know, and as I talked about in the introduction, one of the main drawbacks of eigenobserver is the measurement noise amplification. And so there have been a lot of work in the literature in order to deal with this issue. We can, for instance, cite Astolfi that used LMI techniques in order to reduce the maximum power of the eigenparameter in the designs. And we can also cite another type of approach that is the use of a filter, as done by Zemush. And so the idea is to incorporate a filter in the design of the observer. And this filter will filter the observation error that is made by the observer. And this will lead to mitigate the measurement noise amplification that happens with eigen observers. So that's what will be this approach that will be considered in this work. So to cite another paper, it's with triangle. And so equation 11 presents in a compact way, in the augmented way, a filtered eigen observer. The augmented state is composed of the state estimation of the system, x hat, and the state of the filter, eta, which correspond to a filter version of the estimation error. So of y minus cx. Note that in the state matrix, M, here, we have two gains to design, so L bar and D. The first one is to deal with the observer dynamics, and the second one for the filter dynamics. So the step design will stay quite the same with respect to the previous eigen interval observer that I presented. There will still be 3 main steps to follow, and there will only be slight changes that I will try to highlight. And first, it's on the first step. Now we have 2 gain to designs. So we need the state matrix again to be Hurwitz with distinct pole in order to ensure the diagonalizability. And we parameterize the poles by theta, the eigen parameter. And we also need to check that we are in an unstructured system, the following conditions. So the ID is the same, so we have to design the observer gains, but in practice, it is made differently than in the previous observer. Now, again, we use a change of coordinate based on the C diagonalizability. And this will allow to ensure the cooperativity of the error dynamics in the new base. And once we have that, once we have the observer state in the new base, we are able to design to derive the interval observer structure using the bounds of the uncertainties. And so we arrive to the second theorem, which is the one that presents the filter eigen interval observer. So equation 12 is a filter eigen interval observer, is an interval observer for the filter eigen observer. And again, it has 2 dynamics, one for the center, one for the radius. So I will just move on quickly and say that we have the inclusion properties that still hold. I didn't wrote again the error dynamics because it is really based on the same principle. So we have the inclusion properties that is guaranteed. And again, we need to ensure that the radius do not diverge. And for that, we have again a sufficient condition that is basically quite the same, but we need to make sure that it is also respected. This property is respected when we design such observer. So I will now finish my talk presenting you some simulation that I made. So first is, in the first time, I will present you on a numerical example the behaviors of the 2 observers. And I will especially focus on the influence of the eigen parameter. In a second simulation, I will compare this work, the work I've done, with another interval observer that has been designed. So for this example, we consider the following LPV system. So the same as in the problem statement, and we'll also have the following inputs. So all the inputs will be bounded, and the uncertainties will be unknown by the observers, but we know the observers will know the bounds of those uncertainties. And we also have an uncertainty on the initial condition. So the first figure presents here the result for the the estimation obtained with a certain poles of the observer obtained with theta, the eigenparameter equals to 10. We can see in this case that the estimated intervals are quite large, and as well, they are not really noisy. This is due to the fact that the eigenparameter is not that high, and with respect to the noise. So we can really see the benefits here of the filter. We can only see that they globally have the same dynamics. And now if we increase this eigenparameter theta and we go to 30, we can see that we decrease the interval width for the state estimation. We also increase the impact of the measurement noise in the non-filtered version. So we can see that the blue curve is really more noisy, and the noise has been taken as a sine wave just for simulation purpose. And the last property that we can see is that the convergence is now faster also due to the eigen properties. So we have at the beginning a high, like peaking-like phenomenon, but then the convergence is really obtained quickly. Yeah, so through this example, we have seen that the eigenparameter is able to tune the convergence speed and the interval width up to a certain limit, of course. And that the filter is effective if it is tuned correctly. So now I will move on to the comparison of my observer with another L2 performance interval observer designed by Thibaut Taref, Tarek Raisi, and Efimov. So we consider an LPV system here. It's a little bit different than the one of my problem statement, but they can be written in this form too, so it's not really a problem. So the interval observer that they design looks like equation 17, and the gains, the observer gains, there are two, are designed such that the L2 norm of the transfer between the additional bounds of the bounds of the additional input to the estimated states as a norm less than gamma. So I don't deep into the details of this observer, but this is a general overview of what they have done. And so we'll take this example, the example of their paper. So with their parameters. And so I adapted my design to this one. And this is what has been obtained for a certain choice of gains, observer gains and filter gains too. As the noise is not really high and with low frequency too, the efficiency of the filter cannot really, the use of the filter is not really relevant in this example, but it is still shown here. What we can see is that we really have a much faster convergence speed, as well as at the beginning at least, really tighter bounds, estimated bounds. So we prove that we show the advantages of our type of observer compared to what can be done in the literature and based on one example. So to conclude my talk, so this work, as I told you, has been accepted in the conference on decision control that will take place next week. I have shown the design of a high-gain interval observer, which has the advantage to have an arbitrarily fast convergence, and also the interval width can be tuned by the eigenparameter theta up to a certain value. I show also the design of the gains and the change of coordinates, and the sufficient conditions in order to ensure that the radius do not diverge. And the other contribution is the extension of this observer to a filtered version. So a filter is incorporated sorry, in the design in order to mitigate the measurement noise amplification, which is one of the main drawbacks of the high-gain observers. For future work and perspective, this type of work can be extended to sample and delay measurements, to sample and delay measurements. And also, some more applicative results can be obtained on more concrete systems, such as autonomous vehicle. For instance, I'm working with drones in my PhD. So we have this in perspective to apply it to a concrete system. So that's it. Here are some references that I used. And I will conclude by thanking you for your attention. And if you have any question or remarks, just let me know.
Okay, many thanks, Antoine, for your very interesting presentation. And I already see the very first question from Luc.
Yes,
Directly.
thank you very much for the talk. So I would like to understand exactly what you mean by stability, because at the end of the simulation, we have no convergence to zero. So there is something which converges to zero, or what do you mean here by stability? It's local stability, or?
By stability, I mean that the error dynamics converge to a certain ball. Like we cannot ensure the convergence to zero because we have uncertainties.
Yes.
So we will just ensure that if I see, yeah, that the error dynamics, so which are, let me just maybe up here, that the error dynamics here is bounded.
Okay. So I understand. So it means that you have some kind of distance between your state and the ball that decreases, always decreases.
We cannot ensure.
And once you are in the ball, you get trapped inside the ball and you cannot go out. Yes.
Yeah, like this.
So it's more related, maybe what we call a positive invariant set, no?
Yeah, I think it might be related to this concept. Yeah.
Yes, because after it depends. But yes, for me, probably I would have used the positive invariant set just to show that you will get trapped inside a set. And also, I have another question. It's about the cooperativity. I think so. Of course, you can have some change of basis so that non-cooperative system becomes cooperative, but many systems you cannot probably find such because it does not exist any change of coordinate such that it becomes cooperative. So I would like to know why you say that interval approaches are limited at the beginning to cooperative systems. I think it's not a necessity, or maybe it's related to your approach.
The cooperativity is not required for the system itself. It is required for the error dynamics.
Yes.
Okay. And this is required in order to ensure that we have the inclusion property, which is the main advantage of interval observer. So we have some guarantees about that the state of the system will belong to the estimated bounds. And so, as it is, it can be hard to obtain the cooperativity of the estimation error, of the error. Usually, what is done is changes of coordinate that will ensure this.
Yeah. Okay. Thank you. I think thank you for maybe just at the beginning in your slide number 3. I would like to know why you or number 5, why you ask A to be yes, stop here. Yes, A equal 0 identity and 0 0. So why you ask?
It is just to cope with the canonical observability form. It was just an example to show that for high-gain observer, the design is usually made with based on those type of system. And I didn't wrote the dimensions, but here the zero are not block of zero, but are
okay. And here, for instance, in your x hat dot, the HGA dynamics.
Yeah,
here you have x. It should be x hat. No, in the middle, just in the middle of this formula.
You're right. Yes. Thanks for the typo.
Okay.
Right.
Okay. Thank you.
Okay, then let's see. Do we have any further question? Yes, in fact, I have also 2 or 3 questions. At the very beginning of your talk, you mentioned that parts of your current work are aiming towards the enhancement of real-time properties of your estimator. Could you elaborate on this a little bit further?
Okay. So I inspired my work based on notably this article of Tabet, which is one of my supervisor in my PhD. And so in this article, she used a change of coordinates, so which looks like what I've done. So let me just take it here. So with the omega like this. But the issue that she had is that it was different because the eigenparameter theta here was not here actually. This parameter, eigenparameter, was not considered in this term like this, and so it results that at the end the norm of the change of coordinate of the operator omega, its norm wasn't constant, so it was time varying and it was actually decreasing over time, and so this will cause the like up to when we run a simulation for a certain time, we will have some numerical precision issues that will occur, and so it was not really, it was good for like small simulations, but when we want to deal with real-time implementation and system that run real-time, it wasn't really that good. And that's why I just made some small changes here. And now we can see that the change of coordinates is now as a constant norm, which is the norm of the eigenvector actually, because we have an imaginary exponential, which norm is 1. So yeah, this was what has been solved here.
Okay, and as far as I understand it, you're performing this change of coordinates on the basis of a nominal system matrix A0. Did you also take into account changes or strategies for changes of coordinates that take into account directly the uncertainty of the matrices A and B?
I didn't look at it, no, but it could be interesting. Let me just think about it a few seconds.
Yes, because this is something that a former PhD student of mine did, I think 2 or 3 years ago. This was Julia Kersten who did this at the University of Rostock. And yes, you may look up corresponding references. And she partially also worked with either time-varying changes of coordinates, like in this scenario here, or also time-invariant changes of coordinates, where she searched for point value changes of the coordinates for the uncertain dynamic system.
Okay. So yeah, I'm interested in looking at those references. If you can send me them.
Yep. Yes, I send you the links afterwards.
Thanks a lot.
Yes, and the other question that I have is related a little bit to the outlook on your future work. You mentioned that you want to aim at discrete time measurements.
Yeah.
What will be the fundamental changes that you need to do then in the future work?
If you want to consider so sampled measurements, we will need to add like I would say a predictor. It depends on what you want to achieve with the observer. So if you want to obtain continuous time estimations or discrete time estimations. So if you want to obtain discrete time estimations, so there is no really point of, we just have to derive a discrete time version of this observer. It would be, I think, enough. But if you want to obtain continuous time estimations, we will need to add, I think, like I have this in mind, a predictor of the output that will be used to reconstruct the continuous time measurement based on the sampled one. So that's the idea I have in mind, and that's what I saw also in some references, some articles. Maybe there are other techniques. I don't.
Yes, because the other technique that comes to my mind is something that we recently also had here in the seminar. This was a work presented by Nassim Ramdani, who showed an impulsive interval observer structure. And there what he did is he treated the system dynamics in a continuous time manner with discrete time updates.
Okay.
And this is not a classical predictor-corrector approach, but an impulsive interval observer strategy.
Okay.
And then, as far as I do not see any further questions, let me ask a final one. In your simulation results that you had, it looks as if partially the high-gain interval observer provides partially a little bit better bounds than the filter versions, and at other points in time, it's just vice versa.
Yeah, depends.
Yes, I think it was on the slide 22. Yes, here, for example. There are points in time where the blue one is better, points of time where the green one is better. Does
Actually, it depends on how you design your filter, actually.
Yeah.
Most of the time, I will say that it is more like you should lose, when you use the filter, you should add a bit of conservatism. So depending on how you design it, if you are doing it in a certain way, you are able to obtain this type of result where with the filter version, we have tighter estimations, but they are not really, they are still close to what is obtained sorry, by the high-gain observer. And yeah, I think this is also due to the fact that the inclusion property is guaranteed with respect to the high-gain observers and filter high-gain observers. And so with the filter high-gain observers, we will have more precise estimations of the systems when there are noise. And so that's why we can obtain some better missile estimation. But yeah, if you increase too much the filter effect, then you will add a lot of conservatism, and your bounds will be much larger than the one without filter.
The thing that I was wondering is, since the guaranteed enclosure property holds for both types of implementation, would it make sense to run both observers in parallel and intersect at each point in time?
I don't think so. I think only one type of observer is enough, and preferably the filtered one, because in concrete implementation we always have noise with the sensor. So I think, yeah, the high gain interval observer, the blue one, was here to build the first steps for the design and can now be improved. And the first improvement was to use a filter. Another one could be to use predictors and jumping steps like you talked about, and things like that. But I think running both in parallel on the same system, I can see like this the relevance of doing this, except that it will for sure take a lot of computing resources. So
yes, this is obvious.
Yeah, sure.
Yeah. Okay, thanks. Do we have any further question? See again. If there's someone who wants to ask something, just unmute yourself and go ahead. This doesn't seem to be the case. Then again, many thanks, Antoine, for your interesting presentation, for answering all the questions at the end. And yes, to all of you, I have to wish you now a nice Christmas holiday, because this has been the very last presentation before our holidays, and we'll restart our seminar series in the beginning of January. See you soon.
Okay, bye. Thanks.